This is the second lecture on probability. In this lecture, we discuss on random variables. So in probability, the random variables is a very important concept. So before going to the random variable, we just briefly recall what we done in the first lecture. We have a random experiment, and from random experiment there is some outcomes, and collection of all outcomes is called sample space. So this is sample space. So sample space may we denote like that be a capital omega. Now this is a set of all outcome of this of any random experiment. Now we have a this you can think this as a universal set. You can just think as a universal set. Universal set. There is nothing outside that. Now we have one more thing which is called sigma algebra, sigma algebra or sigma field What is that? That is denoted by, say, script S, and that is called event space. So what is even element of event space? They are all event. So any element of event space is called event, and this implies E is a subset of omega. But this opposite, in the opposite direction, the converse is not true. That script S may not be the whole power set. It's a subset, sub collection of the power set. So it is subset of the power set. So may not be the all subset event. But generally, if omega is finite or countable, we take the power set as our event space. But we can take any other thing. That must be a sigma field with that three conditions. That A belongs to in sigma field, A complement also belongs to sigma field. If the countable collection belongs to sigma field, then a countable union also belongs to the sigma field, and obviously the non-empty. That means that the whole phi and the empty set and the whole omega belongs to the sigma field. That too must be event, and that is called event. And now then we define a function. It's called probability. It's a function from this collection of all this event space to 0, 1 with some property, and that is called probability function or probability measure or simply probability. Now this three together we set as a probability space. This is called probability space. This three things together, probability space. And this omega and A script F is called sample space. Sometimes this is omega is a sample space, and that sample space must you just can't state the what is sample space. You have to state the what is event space also. So sample space and event space will sometimes called sample space. And three things altogether is called probability space. There is a probability, and there is events. We know what are the events, and we know underline the set of all outcomes. So once I have this, we can forget the this what is a random experiment. We can just forget. So the scenario is you have a random experiment, that is a real life thing. You have a random experiment, and from random experiment you can find or generate this probability space. And once you have a probability space, you can just forget the what is the random experiment and what is the underlying probability, what are the randomness. You just forget about all these things. You just think there is a probability space. So once the probability space is there, you can forget the random experiment thing. But if you have a just random experiment thing, there is no such probability is given. Then you have to look on the what is the random experiment and what are the probability. So the theory start with this probability space. So if someone give it to her, this is your sample space, this is your event space, and this is your probability. No need of knowing how this probability space is generated, or from which experiment is generated. You just forget all these things. So in theory, we just start with this probability space. And in real life, there is some experiment, and from that experiment, you have to first generate the probability space. So in problem, you have to find whether the probability space is given to us or not. If it is given to us, good. No need of knowing what is the random experiment. And if it is not given to us, we have to look on the random experiment, and from random experiment, we have to generate. We have to find what is the actual probability space for this random experiment. So this story just start from this probability space, and this all the random experiencing is end here. So new story begins. Now again, there is a one more function. It is called random variable. This x, s is a function. What is this function? So this function is actually as a function. This is from omega to r, and sometimes it's called real valued random variable. Some random variable, if unless otherwise stated, it is real valued. Real valued is we write in bracket, because if I say it is random variable, that means it's real valued. And if it is unless if it is a complex valued or any other vector valued or any other field or any other sigma field, any other set or any other measurable set is then we just say it is a complex valued random variable, it is a vector valued random variable. But if we just say it is random variable, then it is means it is real valued random variable. So what is this? This is basically is a function from that omega to r, the sample space, to real number. Now, just any function cannot be random variable. So it is like must be measurable. X must be measurable. X is a measurable function. So just briefly recall what is called measurable function. So X is a measurable function if there is a measurable space, like here is a sample space, is also a measurable space. What is measurable space? There are two non-empty set, and they are corresponding to non-sigma algebra. And there is a function from this to this. So that means it is a function from some x is a measurable function, say from this to this. What is the meaning of that? That means two things. First of all, x must be a function from is measurable. What is mean by measurable? That must be as a function that must be from omega 1 to omega 2. That means it's take values from the omega 1 and gives output from at omega 2. So inputs are from omega 1 and outputs are from omega 2. But what is the role of this sigma field? The idea is that if you take any b on this script f2 in the right hand side, your inverse image of that must be in script f1. So if you take, say that to say two probability space, for example, and if you have a event on the right hand side, that inverse image must be event on the left hand side. That is the condition. That is the only condition you have to put to be a measurable function. So since this random variable is a measurable function, that means what is the meaning of that? Meaning is that x inverse b belongs to that script s. But what is the coming from b? That b must be a element of sigma algebra on R. But what sigma algebra we have to take? We will take basically this. So this is actually the function from the ordered pair. That this is the input from omega, but you have to look on this script f also, that event space, to the real line, that is a set, and the corresponding sigma algebra is Borel sigma algebra. And if you take R2 or complex number, then there is also Borel sigma algebra is also there on R2 and Rn. There are other sigma algebras also there, but we take Borel sigma algebra on R. That x inverse b for all b belongs to the Borel sigma algebra. That means the Borel set. Now, To check whether this is a random variable or not, this is slightly complicated, because we have to take all the Borel set, and then we have to check whether the all the inverse image is an event or not. So if it is a power set, then it is easy. Since it is a power set, every subset must be event. So X inverse B must be an event. But if it is not the power set, then there's a problem. So what is actually mean by this inverse image of that? So X is omega to R, and what is meaning by if B is a Borel set, it belongs to the Borel sigma algebra, means it's a Borel set. What is X inverse B? X inverse B is nothing but that must be a subset of omega, that set of all small omega, the outcomes such that X omega is equal, so belongs to B. This is the definition. And sometimes we write this as X belongs to B. So X belongs to B, nothing but this set. This is written in the right hand side. And if B is a singleton element, because every singleton is a Borel set, so if B is a singleton, say just a single element X, then we this thing is actually equal to X equal to X. Just we write X equal to X. That means it is X belongs to X inverse the set containing X. And by definition, this is a definition. The right hand side, all this thing on left hand side is a notation. And what is the definition of this? The definition is the right hand side now. What I written now, that is omega belongs to omega such that X omega belongs to the only set containing X. So what is the meaning of that? That means X omega is equal to X. Just X omega equal to X. So this is the notation for this right hand set written in the right hand side. X equal to X. So if I write X equal to 1, that means it's a collection of all outcomes such that X omega equal to 1. It's just X cannot be 1 because X is a function. Actually, what do you mean X equal to 1? That means the outputs are 1. Take all the inputs for which the outputs are 1. The function cannot be 1. Now, what are the Borel set? The Borel sets are, we know it's generated from this type of thing. This type of thing, we generate the Borel set. Now, this is a special type of Borel set. This is Borel set, and for that we write this, and by notation what we write? By notation we write this is X less than or equal to X. X less than or equal to X. And what is this? This is set of all omega. That is X inverse what? This is the X inverse this. There should be one more bracket. And that is set of all omega belongs to omega such that X omega less than or equal to X. Now, this is a set in the right hand side, and left hand side we just write the notation, and this is a Borel set, that all intervals are Borel set, this type of intervals, and everything every intervals are Borel set, and that must be in this collection, that must be event, that must be descriptive, that is the definition. But this is the equivalent condition basically. So once we have this is the equivalent condition. So this is equivalent to this, actually implies and implied by that set of all omega belongs to omega such that if it for all x, this must be for all x belongs to real number. If this is true for all x belongs to real number, then it is also true that it is belongs to B for any B in Borel set, or all B in Borel set. So that is interesting. So if it's true for all B in Borel set, then it must be true for this particular interval, because intervals are the Borel set. But the other side is interesting. If it is true for all this type of intervals, then it is true for any Borel set. And that is actually the proof is coming from, it's just coming from that sigma algebra property, because we know that every Borel set can be represented, can be written is either complement or that's complement of this type of intervals and the intervals and their intersection. There is just union and intersection, and then again union or the complement. That's it. So these are the Borel set can be generated by or can be constructed by that type of intervals using that complementation and intersection and union. And we know that this sigma algebra is closed under this complementation, union, and intersection. So once this intersection, union, and complement is there, the operation that or three type of thing, then this the set which is constructed by this complementation or union or intersection, that is all the also in this sigma algebra. Since script types is a sigma algebra, so once this type of intervals in this the inverse image of that is in this event, their union and their complement, that also in this event. But we have to check one more thing, because what we have to check that. So thing is this: so if you have a two different set, say intervals or set in say in Borel set, these two are Borel set. Now we know, if we assume that x inverse A and x inverse B both in this script test, say A B are two intervals, so whether we have to check their union or their intersection or their complementation, whether this is on script test or not. So is this implies that x inverse A complement or x inverse A union B or x inverse A intersection B, these are in script test or not. So this is the problem, because remember that AB are intervals, but their complement and their union, their intersection may not be that type of interval. Now once this is not a this type of interval, then we can't say that x inverse is also in script test, because we are just assume that this inverse image of the intervals are events. The inverse image of intervals are event. We don't know whether the inverse image of the complement of the intervals are event or not, and we don't know whether the two into their complement take that union of something, union of say minus infinity to 5 closed and union 7 open to minus infinity. 7 open to minus is actually a complement of minus 7 open to infinity. 7 open to infinity is actually the complement of minus infinity to 7 closed. So this is a union of two. Once the left is unbounded, other right hands are unbounded. We don't know whether this union is belongs to that the inverse image is event or not. That we have to prove, and that we can prove because the inverse image of any function has this good property. The property is this: the inverse image of a complement is just inverse image of a whole complement. This is the very interesting property, number one. Number two, it is also true for union, and this is true for intersection also. This is not true for the direct image. This is not true for the direct image. This is the interesting thing, that we take this inverse thing, and this is not true for the direct image. So for direct image may not be true. What is direct image? Direct image is this. For any function, what is the direct image? Direct image is this. So say this is a function from some A to B, maybe. It may not be from omega to R. This may be any set A to B. That if you take a subset of omega now, say subset of omega is say it is A, or you just write on any other notation. Let's say C. If C is a subset of omega, then direct image of C, that by definition, is set of all x omega, omega belongs to C. So this is a direct image, and any D belongs to this right hand side, the codomain. The inverse image defined like that. So it is set of all omega belongs to omega, such that x omega belongs to D. So what are the input for which these outputs are in? And for X direct image, what are the outputs are for every image input from C. Now for the direct image, this is not true. That X of A union B may not be X A union X B. But interestingly, that inverse image actually this occurs equality. And since this equality occurs, and that tells us that the inverse image of any Borel set must be even, because say X in, we know that X inverse A is a even, X inverse B is also is even. That means X inverse A union X inverse B is even. That means X inverse A union B is even because they are equal. So that's why if I just check for only the intervals like that, minus infinity to X closed or open, whatever, this is actually imply that this is for every Borel set the inverse image is even. So no need of checking all the Borel sets. So we have to just check for this open or whatever is closed intervals, any type of, just one type of intervals. So that means we can just refresh our random variable definition. So X is a random variable from omega to R such that X inverse B, that X inverse B, be special type of this set is belongs to this script S, that is even. That means sometimes we write this, sorry, this less than or equal to X omega for all omega. This is a even, and that by notation we write this. Now remember, there is no such now there is no story about the probability. Creating that random variable, no need of probability is there. So just sample space, from this sample space we have this probability thing. We have this random variable. So what is the whole scenario now? We have a underlying sample space, a sample space, and with together with the event space, and from that we construct a probability. We construct a probability thing to that 0 1 is just a function 0 1. This probability defined, remember that probability defines on this script tabs, or just is defined on the script tabs, not for omega. So two things is there. You just think like that. So omega is there, and with omega there is the underlying that sigma algebra. What is the event space? And this is a function from that event space. Now there is a function from omega to X to real number. That is a random variable. And there is the underlying sigma algebra, is called Borel sigma algebra. Now this is there is the inverse image here. So now every Borel set, you have an inverse image in this. So this is the idea. That remember that X may not have inverse function. This X inverse is not the inverse function of X, remember, because that X may not be bijective. Eventually it is not bijective. So since it is not bijective, X inverse, the inverse function of X does not exist, but inverse image of X exists. So there is that inverse X inverse, not from the function from R to omega. It is the function from Borel sigma algebra to the event space. Now we have to complete the story with a probability measure is here. We need one more thing to complete the story. Once we complete the story, then we can forget all the event space and sample space, this scenario. Through this random variable, we just actually have a new story. The story of the sample space and event space stop there, is end there. Like the story of this random experiment end with this. Once the random variable came, once this sample space is there, the story of this random experiment end there. So where the story of this random is end, the story of this random sample space and the event spaces start there. Now there is a two parallel thing. One thing is probability. Probability is no relation with this random variable, and random variable no need of that probability. To define random variable, no need of probability, and to define probability, there is no need of x, that random variable. Now, once this random variable already you just defined, then you can just forget the previous story. But the thing is, the probability is there. So we need a parallel thing of that probability. Otherwise, how, you just cannot recall that, recollect that, reconstruct that probability space. Because if you just write down the random variable and there is no such probability, and you just forget this all sample space or event space, then this probability thing is just lost. So we need a parallel or counterpart of the probability from the Borel sigma algebra to so again it's a measurable function must be. So sorry, not a measurable function, it's a measure. It must be a measure. That x is a measurable function, that probability is measure. So two functions is there. One is measurable function, one is measure. So p is the probability is the measure, and this x is a measurable function. Measurable function is always between two sigma algebras. Now we need a corresponding parallel thing of that probability. And once I get this, we get this, then we can forget all this p, omega, and this script s, the sample space, the probability space. Once we have this, we need something here. Say this is q. We have a q. We have to find what will q will be. Then we can just forget this probability space, and we have a new thing R, Borel sigma algebra over R, and this new probability on Borel sigma algebra. And we change from this to this is via that random variable. So random variable basically change the whole probability space to a new probability space where the underlying probability, the set is real number, the underlying event space is the Borel sigma algebra, and this underlying probability is there, something we have not defined that till now. Now you just think on this probability thing, this R Borel sigma algebra Q. Then we can forget that omega, that's all this sample space are, and this event space and this probability, and obviously the random experiments also. So the problem maybe start from theoretically on this, from this point of view, that R Borel sigma algebra R and Q, and this thing that is called the distribution space. And this Q is called the probability distribution of x induced by P. And we write this as P suffix x. Why we write P suffix x? We just for that P is the probability and that x for the random variable. So if random variable change, that Q change. If probability change, that Q change. So that Q actually constructed from P and x. So this you just replace Q by Px. That is called the probability, the distribution function. Probability distribution is called probability distribution function or distribution of x. Now that is also important, induced by P. So we have P, we have x, and from that we construct Px, that probability distribution of x induced by P. That is important. If the probability is changed, then the same random variable gives a different distribution. The same random variable gives a different distribution because the probability changed. So if you have a coin and we toss the coin, and we have a probability distribution of this on this 0 1. 0 is for tail and 1 is for head. Now, if this the coin is unbiased, say, then it is half a probability, and that distribution is bound only half. And this probability change, if it is a 0.4 with head and 0.6 is tail, then that probability distribution is again bound only, but this p, that's bound only p, that small p, that probability of this head, the probability of 1, that's changed to the 0.4. So distribution change. So what is the story shifted to one story to another story that start with random variable and underline some randomness concept. What is something vague concept, just not a mathematical thing. From there we construct a truly mathematical objects that sample space, event space, probability. Together all these things is called probability space. This probability is a function that omega that is a underline that universal set, and that is a sigma algebra. So it is truly mathematical objects. Random expense is not a mathematical object. So random expense and the outcome is not a mathematical objects. The randomness is not mathematically defined, but this is mathematically defined. You can just start from that. We said, okay, this is a set, my omega, this is my sigma algebra event space, and this is my probability. We can start with that. No need of saying discussing from which random experiment is came. But for every probability space, we can always generate a random experiment. Always. Eventually, if there are two different random experiments, may have the same probability space. May have the same probability space. Now, once I have this probability space, we can always say there is a random experiment. From that, you can find this probability space. That means there are several random experiments actually came to the same probability space. So that means actually squeeze the sample space, that random experience thing. All possible random experiments actually they squeeze all this thing, and they identify some random experiment. So if I have a coin with a coin, toss a coin with one coin and toss with another coin, and if coins are both are unbiased, the random experiment, you can say these two random experiments different because the coin is different, but after all that there is no difference between that. The sample space, the probability is actually same for the both coin, because the both coin have the same unbiased. Again, if you have a two different probability space, the two different random variable can lead to a same distribution. So like that, if you have a random experiment with a coin and it is say unbiased coin, and this head tail is the sample space, and the space is the probability that power set of this sample space, set containing phi, set containing phi, and set containing head, set containing tail, and the whole set containing head tail. That four subset together collection is the event space. And what is the probability? Probability is the probability of set containing head is half, probability of set containing tail is half, probability of set containing head tail is 1, probability of set just probability of the phi set is 0. So this is the your probability space. And what may be the random variable? Random variable, that random variable may be like that. So for example, you just think like that. Your omega is say your just head tail, and this script is the power set of that, and this probability is a function from this. So probability of this phi is 0, probability of set containing head. Remember the probability of not head, probability of set containing head. That is a true mathematical thing. But we write probability of head, and probability of the whole thing is 1. Obviously, these are by definition this should be 0 and 1. Now the corresponding random variable will say like that. Say head goes to 1 and tail goes to 0. Sorry, this goes to 0. Now, what is the inverse image of all this? We know that inverse image of say what is this? So this have 3 different values: 0, half. Sorry. This may be 3 different things: phi, and then set containing 0, or maybe that omega whole thing. When it will be phi, if x is less than or equal to strictly less than 0, then it is phi. If it is strictly less than 0, then it is phi. Because if it's strictly less than 0, that means minus infinity say minus 1, and there is no 0 or 1 included. So this no outcome will be there. If it is contain 0 but does not contain that 1, that will be 0, and if it is contain 1, that even that interval, then must be that whole omega. And then what is the probability of that? The probability is now is clear. So this is actually by notation x less than or equal to x. So probability is now it is clear. It is that there is three values: 0, half, and 1. So 0 is for x less than 0, and 0 this is for 1, and this is 1 for half for that, and if x greater than or equal to 1, then it is 1. So this is underline that probability, and we write that as probability that things p of x, that probability of this set. We can just write px, the probability density, the distribution function of this x. We just write probability of this set. This p and this p is different because this p is on descriptive, this p is on the Borel sigma algebra. Remember this, that minus infinity to x close is a subset of real number, is a Borel set. But x less than, capital X less than or equal to x, this is not the subset of real number. This is actually a subset of the even space because it's the inverse image of that. So we have this corresponding probability distribution. Now consider another experiment, like say there is a shooting or in a goal. And in that case, your omega may be success and failure. The success if goal, and if no failure if the no goal is not occur. Shooting a ball in a goal, and if you have a 50-50 chance for that to be a goal or not, then this create a new sample space, like whose sample space is containing success and probability failure thing, and that corresponding even space is the power set of that, and the probability is just half for both the outcome, the elementary event. Now we can define another random variable omega, that y from omega to that you can write as omega dash. Say. So omega dash to real number, and that like that this failure is say 0 and your success is say 1. And this actually gives the same thing, underlying same this p of y, this probability may be say p dash, this probability this p dash of y is same as actually p of x. The distribution is same. Your random variable is different because your sample space is different. Your probability is different because your event space is different. But the underlying probability distribution, now it is both the probability distribution on the real number and the Borel sigma algebra. These two are same. It is just if x less than 0, then it is 0. Is less than x is less from 0 to 1, it is just 0 close, 1 open, it is half. And if it is greater than 1, then it is 1. Same distribution. That means you have two different space, two different sample space, two different event space, but leads to a same distribution function. And this you just see. This is not for just only example. You can have several examples. You can construct infinitely many examples random experiment which leads to the same distribution, and which called the Bernoulli half distribution. That means once I have this distribution thing, we can forget all this random experiment thing and all this random. Eventually, you can forget the random variable also. No need of random variable because we forget the sample space. We can just the random variable is the utility of the random variable is construct the distribution, probability distribution. So once we have this probability distribution, we just forget all these things. All these experiment, whatever the experiment may be the ball shooting a ball, or experiment may be tossing a coin, or experiment may be bombing, drop a bomb, whatever. Ultimate that probability distribution is same. That means there are a huge number of a class of random experiment and huge number of sample space actually converts to a single probability distribution. That means there are several, all possible infinitely many choices of your random experiment or the sample space, but your distribution thing is not that much. It is very few or less type of distribution. And this type of distribution, which is coming from the real life scenario, is called the theoretical probability distribution. What are the theoretical probability distribution? The well-known theoretical probability distribution is start from Bernoulli distribution, after the name of Johann Bernoulli, I think. There is called Bernoulli family. There are three Bernoullis in their family. Bernoulli families are in mathematics and physics, there's there are 3 Bernoulli which are greatest among the greatest. So in the same family, the 3 Bernoullis is very interesting. And Bernoulli family is a very interesting story. By the way, and then Bernoulli distribution, then is binomial distribution, the extension of the Bernoulli distribution, repeated success failure experiment. Then there are geometric distribution, uniform distribution. Then these are all these are finite discrete distributions. Then infinite discrete is Pomoso distribution, then what, negative binomial, and then continuous distribution is a normal. This theoretical distribution is coming from the real life. There's a finite geometry. There is a finite thing is hypergeometric distribution. These are called there are few such things. Random experiment. This real life scenario is an infinite thing. So once I have this problem on real life, we have to just find the proper random variable. We have to identify the probability distribution is this. Which probability distribution can demonstrate this random experiment? You have to just first thing you have to find our known probability distribution by which we can relate that random experiment thing. And once we relate, we just forget this random experiment story. So once we have the distribution thing, we just forget all the previous stories. So there are 3 different stories, and we land with a new story. Start with a new story. It's called probability distribution, and we just forget that the random variable, all these things end there. Now, once this probability distribution is there, we can generate a random variable. And that generation of random variable is not the unique. You can think on different type of random variable. Ultimately, these are the same thing theoretically. And there's a new stories we begin. What are the expectation? What are the variance? What are the other skewness, kurtosis? All these things for this random that is theoretical probability distribution may not be theoretical. There are some other sampling distribution called the chi-square, t, beta, gamma. There are other distribution called sampling distribution is coming from the sample when you sample take from a population. But theoretically, these are the well-known theoretical probability distribution. And if someone give me, okay, this is a Bernoulli half. If Bernoulli half means there is nothing, no story on this random experiment, nothing on this random variable. So someone give it is Bernoulli half. What is the meaning of the Bernoulli half? That means there is some random variable whose distribution is then Bernoulli half. And okay, let's take that as x. That means x is random variable which follows the Bernoulli half. So we write like something like that. X follows that distribution px. We write this is called follows. The tilde notation is called follows. We write that. So x follows this probability distribution. That means that x also may not be given to you, given to us. The distribution is given. Okay, consider the normal distribution. Consider the Bernoulli distribution with half probability. That means we take, okay, this is we have a random experiment, a random variable x which follows this Bernoulli half. What is the meaning of that? The meaning is this: x can take 2 different values, 0 and 1, and that all the values x can take, that is the x of omega, that the range of this range of x is called spectrum of x. Spec of x for x is discrete. X is discrete. If x is discrete, and that discrete means this set is actually countable or finite. That means is a countable or finite, or countable. That is called spec of x. And if it is a continuous, then it is called support of x. Where the density is positive, that is called support of x. Support of x means the density is positive. And spec of x means it is for the discrete case, support for the continuous case. Spectrum of x means it is the all set of all outcome for which output, that output of this x for which the probability is positive. And for continuous, the every point the probability is 0. That's why we can't consider talking about the spec. It is called support, where the density is positive. We'll discuss later on what is discrete and what is continuous random variable. Now, once we have this Bernoulli thing, and we can say, okay, we can take a x. One can take x, one can take j, whatever y, but x equal to 0 is just half, and x equal to 1 is just half. And if someone asks what is a random experiment, random experiment may be anything. It may be shooting a ball on the goal post, or shooting a tossing a coin with a unbiased coin, whatever may be. Ultimately, this leads to this Bernoulli half distribution. So there are three different stories. One is just from the random experiment and all this thing, randomness, which is actually the real life thing. Then there we can just true mathematical objects with probability space, and then our underline we one more change on that, and which is more useful to us, and which is less complicated, and which is very few in nature. There are some few thing that is called the probability distribution. So this start with the probability distribution, random variable and their probability distribution. We in this lecture we actually discuss on that, and next we discuss what is the what are the distribution mean expectation and variance, and what you should interpret that. One thing is you have a random experiment, and from that you have a probability space, and from that you have a probability distribution, and everything in the probability distribution you have to interpret what is the interpretation of that in this real story. If okay, I have a random experiment, I have a probability space, sample space, everything, and from that I generate a random probability distribution, and we know what is the what is the expectation of the distribution. So its expectation is 7. Now we have to interpret what is the meaning of this expectation 7 in the real life. That's where the story started. The story started from the random experiment. What is the meaning? What is the actual meaning of that? This probability distribution has expectation 7. What is the meaning in the real situation? Where the story began. That random experiment thing. So what is this meaning of expectation 7? What is the interpretation? What is the meaning of this for this particular random experiment? There is a relation through this random variable. And you have to interpret that. So in a real life, you have a random experiment, and you ask you some question. So what is this? What is that? What you have to do? You have to just change this story to a different framework through this random experiment, random variable, this sample space, and then to the probability distribution. And so once we have it in the probability distribution, we know what are the probability distribution. We know theoretically beforehand, before this problem, we know in our class that what is the expectation, what is the system, what is the cutoff, what is the variance, and then we have to interpret that result, that theoretical result, on this real life. That course, nobody is interested with the theoretical result. Remember, nobody is interested. Everyone is interested in the real life thing. So that means you have to interpret your theoretical result in real life. Otherwise, there is no utility of all these theoretical things. Unless you can't interpret what is this result. Theoretical, okay, this theoretical we have this by definition we have this value is 7. But what is the actual meaning of that in real life? If someone do not know what is sample space, what is event space, what is probability, what is random variable, what is probability, someone do not know this. But you have to interpret that person also. What is the meaning of expectation of 7? Who don't know all this thing. Just he or she knows just what is the random experiment and what is this thing. This is something shooting a ball in a goal post. That everyone can understand. But you have to interpret your theoretical result in their terms, who don't know all this probability, random experiment, random variable, everything. You don't know. You just know what is the random experiment. Eventually, you don't know the term random experiment. You know the random experiment. Okay, tossing a coin. You just say, okay, there is toss a coin twice. You don't know the term random variable. You know the random experiment. But without knowing the term random experiment, you have to interpret in their language also. That is the main idea. Unless in any interpretation, there is nothing is just useless. All this result. So this thing and these results are the inverse image of this A union B. This is like as a homework. This This you have to check in your own. This all these three results you have to check. This is the homework for you. You have to check all these things. And just okay. And the one thing is this: you have to interpret all this set thing in their corresponding notation. So what is this? This is collection of all such x omega less than strictly less than x, and you can write is a union of we know in the measure theory lecture. This is nothing but this set of all x less than or equal to. You should write the all open intervals in terms of closed interval, because we know what are the probability of this closed interval. So right hand side, we know what is the probability of the right hand side. So, but we don't know what is the probability of the open set. Similarly, you can write the closed set also in terms of closed intervals in terms of open intervals also. That is actually so. And you have to check. This is check yourself. So. Okay, this is for today's lecture, and next we discuss on the probability distribution and their different properties of this probability distribution function, and then go to the what are the discrete and what are the continuous concept, and then probability mass function, probability density functions, different functions on that, and what are the different functions for the different probability theoretical distribution like Bernoulli, normal, all this thing, and then go into the expectation moments and other things. That's all for today.